Hi, so this is this is section 3.8 on exponential growth and decay, and it's the second part. So these are the last two examples. Here we have a sample of, this should say tritium, that is a hydrogen ion. Ion? Maybe. Okay, I think so. Is decayed to 94.5% of its original amount after a year. So what this is telling us, this is how we're going to find K when we go to find K. So we know that decay follows our model. So we know we're going to have y equals y naught e to the kt. And this 94.5 means that y equals 0.945 times y naught when t is 1 year. So t in years. Make sure, especially if we have a take-home type of exam on this, that you always write what units your answer is in, and also anytime you're making a model, you want to make sure that you say, and this is so y is the amount of tritium, which is, I think what tritium is a hydrogen ion that most hydrogen ions have either no electron or one electron. But I think you can force it to have three. Not sure though. You probably should look that up. Okay, so for part A, we're asked, what is the half-life? So half-life is the amount of time that it takes for the chemical or the compound, or in this case the ion, to decompose to where you only have half of the initial amount left. So half-life is when it's a time, when y equals half of y naught. That's what half-life is. Okay, so what is the half-life? We will have to figure out what k is in order to do that. So we're going to use this information right here and this model. We have t, we have y in terms of y naught, so the y naughts will cancel, so we'll be able to solve for k. So what we have is y, which is 0.945 of y naught, equals y naught e to the k times 1, so e to the k. Our y naughts, we can divide both sides and they reduce to 1. And so we can also take, we have e to the k equals 0.945. So that means k is the natural log of 0.945, which is approximately, I don't know. I'll go ahead and put it into the calculator. So that is approximately negative 0.0566 if we round 4 decimal places. Okay, so what we want, now that we have k, we know that our model is y equals y naught, which was, well, that's just y naught. That's okay. We don't need it. But we have e to the negative 0.0566 t. Again, notice that k is negative, and that is indicative of decay. So we have our model. We want to know the half-life, so we're going to replace y with 1/2 y naught. And then our y naughts will cancel again. Again, if we're given percentages, then we don't really need specific amounts. And so then we're going to have e to the negative 0.0566t equals 0.5. And so if we take the natural log of both sides and divide by 0.0566, we'll get t is approximately natural log of 0.5 over negative 0.0566. And that is approximately 12.25 years. Again, make sure that you recontextualize problems. So let's go ahead and go up to B. That's the half-life. So the half-life of tritium-3 is 12.25 years. For B, how long would it take the sample to decay to 20% of its original amount? So for part B, this is a half-life of sorts. We could get y equals 0.2 y naught. And if we plug this into our model here, we have 0.2 y naught equals y naught e to the negative 0.0566t. So then we get rid of the y naughts, we divide both sides by 0.2, we exponentiate. Let me see, am I missing something? We're solving for t, so no. So let's go ahead and do this. We actually don't want to we don't want to divide by 0.2, we want to divide. So I want to take the natural log and then divide by negative 0.0566. So I've got t is going to be equal or approximately equal to ln 0.2 over negative 0.0566. And so that is going to be 28.5 years. Okay. Which makes some sense. If the half-life is 12 years, then the 20% life, hold on. Let's make sure that this makes sense. Half-life, so 50%, and then how long would it take the sample to decay 20% of its original amount? To 20% or decay 20%? It says 2. Okay. Decay to 20%. That would make a difference, right? If it were to decay 20%, then you'd have 80% left. But as it turns out, we wrote that down correctly. We wanted 20% we got for the second part. And if it's decaying to 20%, then we are actually losing 80%. So it does make sense that this is longer than our half-life because we're losing 80% instead of losing 50%. So, okay. So this next example is has Newton's law of cooling. This is also defined by a differential equation. We have the rate of change of the temperature. So capital T is for temperature, and dt, the lowercase t, is time. And that is pretty conventional. So the rate of change of temperature with respect to time is equal to a constant times t, which is temperature, which is our function. So the capital T is our y, minus T sub s. And you can see here that T sub s is the surrounding temperature of the medium. So that's the differential equation, which describes the rate of change in temperature of an object. And if we let y of t equals t minus ts, then dy dt equals ky, which means y of t equals, if you can see what's going on there, is basically Newton's law of cooling is similar to our exponential equation. You notice this is like the solution to this differential equation, except for that they replaced this t minus ts with y. Okay. So we're using the same model. We just have to be careful because y is actually, when you want to do, when you want to find y naught and such, you've got a different value. So let's go ahead and take a look at number 4. I think I want to write these down though, just the ones that we're going to use. So we're using y of t equals y naught e to the kt. But y is t minus ts. So y naught is also going to be t naught minus ts. That's going to be initial temperature. Newton's law of cooling is used for things like if you were to bake a pie and you want to know how long before it's cool enough to eat, that obeys Newton's law of cooling. So when you talk about the surrounding temperature of the medium, that's like in the example of the pie, that would be the air surrounding the pie. If you were working with metal at really high temperatures to mold it, you might stick it into like cold water, and that would be the surrounding temperature of the cold water. So the medium is the surrounding medium, whatever the object is in. And Newton's law of cooling, Ry, is the, let's see, Ry here is temperature minus surrounding temperature. So let me go ahead and leave it like that. Let's go ahead and do this example. So in a murder investigation, the temperature of the corpse was 32.5 degrees at 1:30 p.m. And I'm going to do a different color here so we can keep it straight. 30.3 degrees Celsius an hour later. Normal body temperature is 37 degrees Celsius, and the temperature of the surroundings is 20 degrees Celsius. When did the murder take place? So this is provided that the murder took place somewhere where there's controlled temperature, like inside, then which makes sense. 20 degrees is close to 70 degrees, so that's like indoor temperature. Then this is actually something that you could use to estimate time of death. Okay, so what we have here, I want to pick up the information here. So we're going to have this model. We're going to use this. And so, first of all, this 37 degrees, well, let's not use that just yet. I want to start with this 20 degrees. The temperature of the surroundings, that's probably the easiest one here to pick out. That's Ts equals 20 degrees. I'm not going to bother with the 0.0. And at the time of death, we have 37 degrees. We also have what amounts to a couple of ordered pairs. So we know if we have, let me just write it like this, T, comma T, we have 32.5, comma 130. So let's go ahead and make that 130 our initial time. You always want to make your initial time something tangible. So even though the death happened before the finding of the body, you don't want to make it your unknown to be your initial time, because then that doesn't give you your why not. Okay, so we're going to call it 0 initial time. So like if we had we have a function y, but we're saying y, whoops. T of 0 is going to be 32, 32.5. And so y, which is T naught minus TS, is going to be 32.5 minus the surrounding temperature, which was the 20. So 12.5 degrees. Okay. So at 2:30, that's my hour later. So what we have is T of 1. Again, I'm using this because they're giving us information about T, and TS is constant. So, but in order to convert it to Y, we need to make sure to subtract that 20 degrees constant. So at T1, that is when we are 30.3 degrees Celsius. And so if we look at our model, well, actually we don't need to look at our model just yet. We need to find Y of 1. That's going to be 30.3 degrees Celsius minus 20 degrees. So that is, let's see, 9.7 degrees. Okay, so let me go back up here really quickly because I think this wasn't just Y. This was actually Y naught. And let's see if we can put our stuff together. We're going to need to find K, and it's this information that's going to give us K. So we've got we've got 9.7 equals, so here's what I'm doing. I'm looking at this model, and then I'm putting in Y naught, and I'm putting in 1 for T, and 9.7 for Y. So 9.7 equals 12.5 times E to the KT. T is 1, so this will just be E to the K. So E to the K equals 9.7 divided by 12.5, and K is natural log of 9.7 over 12.5, which is approximately negative 0.25. So does it make sense that our K is negative? Are we decaying? Let's see. The why is the difference between the surrounding temperature and the temperature? So is that getting smaller as time goes on? It is, because the temperature of the body is approaching the surrounding temperature. At some point, you go to equilibrium, and then the corpse will be the same temperature as the room. So negative makes sense. So our model is now Y equals, we have our Y naught, and that's not going to change. So Y equals 12.5 e to the negative 0.25. I should really, actually, I need to put more decimal places in. 0.2536 times t. You never ever want to over estimate k. It's in a position where it's going to magnify the error. Just like, you know, if you have an error and you put it into a formula and you multiply, then the error gets multiplied. And so here you're exponentiating the error, and so it really, really compounds it. Okay, so when did the murder take place? That's where we're going to need this 30. Okay, so I need to go back and cross out this piece. This is not the time of death because this is what normal body temperature is. Okay. The corpse, this was time of death. Okay. So the initial time is time of death. I'm sorry. No, this is not. Oh my goodness. I'm not starting over. Damn it. Okay. All right. So we have our model. And then we want the time of death. So we want t when the body was normal. Okay. So we're just going to sub in 30. Actually, before I do that, remember this right here isn't capital T. It is capital T. So t minus t naught is 37. This is what y is. 37 minus t naught, which was 32.5. Let's see, 37 minus 32 is 5, so 4.5 degrees. So we're going to have 4.5 equals, now I'm going back to my model here, 12.5 e to the negative 0.2536 t. We're going to solve that for t. And so we've got e to the negative 0.2536 t equals 4.5 over 12.5. I'm going to save the calculator work for the last step. So t equals, I'm going to take the log of both sides and then divide by the negative 0.2536. So I'm going to take natural log of 4.5 over 12.5 and then divide by negative 0.2536. And this should give us our answer. Negative 4.03. So negative is good because death happened before the initial time. I know I spelled initial wrong there. Initial. Okay. And initial time was at 1:30. We're just going to call this 4. So this will be 4 hours before 1:30. So let's see, 12:30, 11:30, 10:30, 9:30. So 9, 10, 11, 12, 13. Yes. So 9:30, and this must be AM. Wait. This was at 1:30 p.m. So yes, this is at 9:30 a.m. And that's time of death. Okay.